We continue our discussion of rotational motion by introducing the concept of torque. And torque is the rotational analog of force. So it's rotational analog of force, much as we've had rotational inertia being the analog of mass, or angular velocity being the analog of regular velocity. We're going to shift our attention from force to this idea of torque. And the symbol for torque is a little lowercase tau. It's like a T, like a little mushroom, or like a T with an umbrella handle on it, a tau. And the important point is that torque causes things to rotate in much the same way as forces causes things to move or to accelerate. And so here we've got some beam, and I'm going to note that we've got an axis right here. It's always important in rotational motion to know where your axis is. And I'm going to apply a force F at some distance r away from the axis. And it does actually matter how far away from the axis you are. Now notice, I can actually declare a little angle here. I can actually declare this angle, which I'll call phi in this case. And the torque that this force generates is going to be equal to the distance away from the pivot times the force F times the sine of this angle phi. And I want to note real quick, why sine? Why is it sine? Well, in this case, we can always interpret these sines and cosines and different things as also being components. So in this case, I want to note that if I do F times the sine of that angle, what I'm really getting is the perpendicular component of my force. That is, this is the same as saying the distance r times the perpendicular component of my force. And why only the perpendicular component? Well, just like for work, how we only wanted the parallel component, because that was the part that was going to make things move. In this case, hopefully it makes some intuitive sense that the perpendicular component is going to be the component that causes things to rotate, and that the other component, the parallel component, isn't going to cause this arm to rotate, right? That's just pulling directly on it. So only the perpendicular component generates torque. A couple things to note about torque here. It does have units of Newton of newtons times meters, as its name would suggest. It is important to note that the r in this equation is the distance from the axis to where you apply the force. So if your force is not applied directly at the end, right, let's say I instead applied my force here, my torque would be different because I'm not as far away from the axis. It also is a vector. It does have a direction. And in fact, you will see sometimes that more mathematically, instead of being written as RF sine theta, it will often be written this way, that torque is a vector equal to the vector cross product of r and the force. Now, we haven't talked a lot about vector cross products. This is the other way to multiply vectors. We've talked about dot products so far. And you might remember dot products were the magnitude of the two vectors times the cosine of the angle between them. Here, a vector cross product has a number of interesting properties which we're not going to go into too deeply in this class. But it is important to note that for any vector cross product, right, A cross B, it's the magnitude of A times the magnitude of B times the sine of the angle between them, which you'll notice is exactly what we have here. And they do have a direction given to us by the right-hand rule. And the way you use your right-hand rule in this case is you put your four fingers in the direction of the first vector. You curl them towards the second vector, and your thumb gives you the direction of the cross product. As an example of this, let's take a look at a little wheel here. Let's take a look at a little wheel here, and let's say we've got its axis running through it this way. It's a little wheel on a spindle. And let's say I apply a force off in this direction. Well, there's the radius from its axis over. So if I take my four fingers and I kind of point my four fingers up along the radius, and then I curl them this way towards my force, my thumb is forced to point along the axis. And so in fact the torque vector is along the axis. And I just want to note that this is actually the same direction as we've been considering for omega and for alpha. That is, if you kind of think about which way a torque wants something to rotate, your right-hand rule will give you the correct direction. So here, this is going to want to rotate it counterclockwise, which is going to be up. And in fact, typically we would say that a positive torque is counterclockwise as seen from above, a negative torque is clockwise. And you can also have torques of 0, as noted. So in this case, right, pulling this way would be a positive torque. If I pull down this way, this would be a negative torque. And if I pull directly radially, anything that's directly radial doesn't cause it to rotate at all, and so it would give 0 torque. So like as a quick example here, right, let's take a look at something. Let's imagine that we have, here's our axis. Let's imagine that we have a stick of length L, and we are supplying a force up this way on it. And let's imagine that this stick is currently at some angle theta relative to the horizontal. And I want to know what is the torque here from gravity, and what is the torque here from my force F? All right. Well, let's take a look at gravity first. We know it has a magnitude of mg. The question is, where on my stick can I put it? My stick extends a whole distance L. And here's where, this is one of the key things about rotation, is if you're going to pick one point to apply gravity, try doing it at the center of gravity, or at the center of mass. So we get a force of mg down there. So if I want to know the torque that gravity is applying, all I need is to look here at, and I will be honest, I generally prefer to look at the perpendicular component rather than relying on RF sine phi. And the reason I don't like to rely on RF sine phi is that this sine is only true if it's a very particular angle. Sometimes you will in fact end up with cosines because we've been given a different angle. So I prefer to use the second method to do the radius times the perpendicular component of the force. Well, if I look at gravity, it's being applied halfway down, right in the middle of the stick. So that's going to be at a distance of L over 2 from the pivot. And then what's the perpendicular component? Well, you might remember from back from inclined plane days that perpendicular component here is in fact going to be mg cosine theta. So our total torque is 1/2 mgl cosine theta. And I want to note, again, cosine theta makes some sense. If my angle is smaller, gravity gets more perpendicular. That is, as my angle gets smaller, that gravity force vector is better aligned and gets me more torque. My force F is obviously at the full distance L. It's all the way at the end. And it does have a total magnitude of F, but we got to kind of do a little bit of figuring about what the perpendicular component is. I'm actually going to help myself out. I'm going to move F up here and note that I'm looking for this component. So let me see. Which is going to be theta? If this is theta, this is 90 minus theta, which makes this 90 minus theta. So this is also theta. That makes sense. So in this case, it's also going to be m or L times F cosine theta. Yes. L times F cosine theta in that case. So sometimes you'll get a sine, sometimes you'll get a cosine. If you focus on just making sure you get the component of force perpendicular to the radius, you will be in good stead. Here's the question, what do torques do? Well, torques cause things to rotate, but you might guess, based on the fact that there's some kinship here with Newton's, with the idea of force, that we might get a little Newton's second law action going on, and indeed, you are right. And so, in fact, in general, we got to remind ourselves that instead of F equals ma, we are now going to get this very, 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 very all-important equation. Torque equals I alpha. And this is Newton's second law for rotation. Torques, what do torques do? They cause angular acceleration. Torque equals I alpha. So this is a very, very, very important equation, just like F equals ma is. And so we're going to use it a whole bunch. So I want to do a little example of how to apply torque equals I alpha. And what we're going to do is we're going to imagine that we have a stick. We're going to imagine that we have a stick. And that stick is going to be suspended from the ceiling. It's like down on a little string or something, which is tied around the pivot. And this stick has a mass m and a length L. And we're just going to kind of suspend it. It's balanced at one end, and we're just going to let the other end drop. We're going to drop it from rest. And I'm going to ask a couple different questions about this. So the first question I'm going to ask is, if I just drop it, what is the initial angular acceleration the moment we drop it? What's the angular acceleration of this mass? Well, first we have to go and look at some of the forces on it, right? Free body diagrams are still our best friend. We're going to have some tension, presumably upwards here. And then we're also going to have gravity. And here, when we're doing these free body diagrams for rotation, it's really important to actually put forces where they go. Put forces at the point of application. I know we used to draw them back and forth in our unit on forces. We would just draw them on a dot from the center of mass. Here we're actually interested in where they apply, because it does change the torque. In this case, if we look at our net torque, our total torque, we're going to have some positive torques and some negative torques. So again, our positive torques are going to go in the counterclockwise direction. In this case, we actually don't have any positive torques. We only have a negative torque. I guess I could take this direction to be positive. If I wanted, I can really take any direction to be positive. It's important to note here that gravity here applies a force of mg L over 2, because it's a force of mg, it's at a distance of L over 2, and if you'll notice in our current configuration, it's perfectly perpendicular, so we don't have to worry about perpendicular components. What about the torque from our tension? Now it's important to note the torque from our tension is applied at the axis. It's applied where the thing is attached. So the R for this force is 0, and therefore the tension force actually applies no torque. It's just applying a force that's supporting it, but it's not actually going to make it rotate. So here's our torque. That's going to equal I alpha. Now we happen to have a stick supported at its end. So I know that that's going to be 1/3 ml squared times alpha. And now I get to just do some nice little things. One of my L's cancels, my M cancels, and I can do a little bit of multiplication. And I end up with my initial angular acceleration is in fact 3g over 2L. 3g over 2L. So I get a little bit more angular, I get a decent amount of angular acceleration there as the thing starts to fall. What if instead I asked a different question? What if I take the same stick? Still mass m, still length L, still suspended at one end by this string. And instead what I said is I'm still going to have my tension force and I'm still going to have mg. And what if I said that I wanted to apply a force to it in order to keep it from falling? And just for the sake of being silly, I'm going to apply this force down here at a distance of L/4 from the end. All right, what if I want it to stay still? Well, in this case, we actually really need to consider two things. And this is a really big part of what happens in the unit on rotation, is often we need to consider both torque equals I alpha and F equals ma. Sometimes we need to consider both of those. And let me show you what I mean by that. Let's say I wanted to find this force F. If I just look at the F equals ma perspective, right? All my forces are up and down. I'm going to have tension and my force up and mg down. If I don't want it to move, if I want it to stay still and be in equilibrium, this has got to equal 0. Well, so I get force equals mg minus t. Well, that doesn't really help me because I don't know t either. So let's see if we can do something else to help us out here. Let's instead consider torque. Now again, if we look at our torques, it's definitely the case here that our tension still applies no torque. So only F and mg do. Now F is being applied at a distance of 3L/4 from the axis, because if that's L/4, this is 3/4 L. Mg is still being applied at L/2. And we need those torques to add up to 0, because again, we don't want it to move. We don't want it to slide or to rotate. Well, at this point, I get 3LF/4 equals, 1/2 mgl. I can do a little bit of cancellation. My L's go away. I multiply over by 4, and this becomes 2. So what I find in the end here is that F equals 2/3 mg, which hopefully it's clear makes tension the other 1/3 mg. So I've solved this little system of equations, and if you think systems of equations are bad words, you better get over that. I've solved this little system of equations to find that whatever the weight of the thing is, if I'm supporting it 3/4 of the way out, I only need to apply 2/3 the weight of the object. Tension's going to supply the rest. So the two of them add up to be the correct a full mg to balance out gravity so the thing doesn't fall, and the torques from force and gravity balance out so the thing doesn't rotate either. So again, we're going to do a lot more in class with torque, but if you take nothing else away, the most important things for you are that torque is equal to the perpendicular component of a force times the radius from the axis that it's applied, so r times f, and that usually we need to consider both torque equals I alpha and F equals ma to understand the true range of motion and the equations of motion for a real complex object.